Hello everyone, today's topic is live sound. The first thing we'll talk about are stage monitors. I want you to understand the function, setup, and routing involved in using stage monitors. There are two main types that you're going to see. This is in order for the musicians to hear themselves on stage while they're playing if they need some sort of reinforcement in order to hear themselves. The first on the left is a wedge monitor. It sort of sits at an angle on the floor and fires sound upwards at an angle towards the musician. The second, and increasingly more popular these days, are in-ear monitors, which are essentially just headphones. These headphones are often of the earbud type so that they're relatively inconspicuous and sort of stay out of the way visually, but they may use various methods in order to also isolate the musician from the sound on stage so that the mix can be created without too much interference from acoustic sounds. Quite frequently, these in-ear monitor systems are wireless so that musicians have easy ability to walk and move around the stage, but they could be wired. Because they're wireless, you're going to need a transmitter as well as a receiver that the headphones are going to be plugged into, and these operate in very, very similar ways to wireless microphones. When it comes to routing to monitors, typically what you're going to use is the aux sends on a console. So we have a variety of mic inputs coming in on the console. We'll create our main mix using the main mix bus, which will most likely be coming out of the stereo out to the console and feeding the front of house loudspeakers. These are the loudspeakers designed to project sound to the audience. Often, the musicians are going to want to hear a mix that is not the same as the front of house mix, just like you have in recording. Therefore, just like we do in recording, we build the monitor mix using the aux sends. Often these monitors are mono if they're wedges or stereo if they're in-ears, but an artist might want just a mono mix in their in-ears anyway, so you may only need a single aux. But the idea is that the number of auxes that you have indicates the number of discrete separate mixes you could create. In this case, we have 4 auxes, so we could feed 4 separately mixed monitors on stage so that 4 different mixes could be delivered. But it doesn't mean that you can't have 4 monitors with a single aux track, it's just that all monitors will be receiving exactly the same signal. Most monitors, most stage wedges, have an output as well where you can pass the signal from one monitor to the other in those particular setups. A lot of the time you're going to be wanting to set up your aux sends pre-fader in these particular circumstances so that the monitor mixes are not being influenced by the main fader position as you do your mix for front of house. If you think about it, when it comes to taking the signal from the microphone to the stage monitor, there's actually multiple places where you can adjust the gain. There's the preamp, and then after the preamp you have the aux send itself, and then often you'll have an aux master, and then finally it's quite typical to have a volume control on the monitor amplifier. That amplifier could be separate from the speaker, or most commonly today the amplifiers are built right into the speaker and you're going to have a volume control on the back of the speaker. There is definitely a proper way to set up this gain staging, just like you do with recording. The preamp knob should be set to optimize your input level so that it fits perfectly within the input meter headroom. Same idea as recording. You don't want to record with the preamp knob too low, or you're going to end up with a high noise floor and not enough signal. And you don't want to record with the preamp knob too high, or you might get distortion if the performance gets particularly loud. So you want to find that happy medium where the majority of the sound is averaging right about in the middle of the input meter. The aux send, you can consider it like your faders in a main mix, should be somewhere around unity, somewhere around 0. However, it makes sense that you're going to have to adjust that up and down in order to actually create the mixes from these various inputs that you have. The aux master, just like the master fader on your normal mix bus and recording, should also be set around unity, but you can use it for small volume adjustments, overall volume adjustments up and down from 0, but I wouldn't go too far from 0, otherwise you're starting to abuse this gain staging chain. Finally, the place where you should set the volume of the monitor sound on stage is the monitor amp's volume. If you're doing your sound check and the artist asks for just a tiny bit more level in the monitors, then you could probably go ahead and do that with the aux master, a couple dB up, 3 dB up. But if you find yourself getting far from 0 dB, you're up at plus 12, for example, on the aux master, I think it's time to bring the aux master back down to 0 and go and make the volume change on the monitor amp itself. If your gain staging gets too far out of whack, if your preamp level is not set right, or your aux sends and aux masters are getting far away from unity, then you risk having gain staging problems, which is most of the time either added noise to the recording or added distortion to the recording. The next most important topic in live sound is feedback. You need to understand what feedback is and how it's generated. Also, you need to understand how it can be reduced, most importantly with an equalizer or sometimes a phase reversal. So feedback occurs when we have a loop in our recording chain or in our live sound chain. In recording, this actually doesn't happen too often because the speakers where we're hearing our sound is often in a separate room than the microphones. However, sometimes when you open up that talkback mic and you have a microphone in the same room as a speaker, we can get a feedback loop in recording as well. However, in live sound, we pretty much always have the potential for a feedback loop. We have artists on stage being picked up by microphones. That signal is being sent to a mixer. That signal is being sent to an amplifier. That signal is being sent to the speaker, and the speaker and the microphone are in the same room, so that speaker signal is being sent to the microphone. So ultimately, we have a loop. We have a feedback loop. Now, a lot of the time, this is not really a problem. What we do is we try to minimize the amount of speaker sound that gets into the microphone such that the overall gain of this loop is less than 0. Less than 0 dB. We need a negative number in this loop. The moment that this entire loop has a positive gain, then the signal will actually keep getting louder and louder and louder by itself. And I think you're familiar with this feedback sound already, most likely. So what you want to avoid is having positive gain in this loop. There will always be some positive gain in the preamp chain here. Often unity gain going through the mixer. There will always be some positive gain in the amplifier. What we're counting on is the negative gain from the speaker to the microphone as the speaker sound drops off as it travels through space. We're counting on that negative gain to be less, to be more negative than the positive gain that we've added with our microphone and amplifier in the circuit, such that the overall gain of the system is still negative and we don't get sound that grows and grows and grows. In practice, when feedback does happen, it tends to result as a single ringing frequency or several ringing frequencies. There's a reason for that. The reason is that this loop that we just looked at is not anywhere close to a flat frequency response. And there will be some ranges of frequencies that will have more gain overall in the loop than others. For example, the microphone doesn't respond equally to all frequencies. How would you expect this system to start ringing at 20 Hertz when the microphone has hardly any sensitivity down there? What we would expect more is somewhere ringing in this mid-range from 200 Hertz all the way up to about 15K. And there's even some boosts up here in the 6 or 7K range. So this microphone might actually trigger high frequency feedback partials before it triggers mid-frequency feedback partials. But that's not the only frequency response in the chain. We also have to worry about the frequency response of the mixer, which should be pretty flat. But then importantly, the frequency response of the loudspeaker. That is very rarely flat. Once again, there's usually a low off in the low end, and a roll off in the high end, and some sort of bumpy roller coaster along the way. And these two frequency responses will superimpose on top of each other so that maybe some dips in this range cancel out peaks in this range, but in some cases you might get peaks adding to peaks. Therefore, you might have much more gain at a certain group of frequencies than another group of frequencies by combining this microphone and this loudspeaker. But once again, we're not done. We have to take the frequency response of the room into account as well, which usually represents the largest deviations in frequency response. If you look close enough at this graph, what you're seeing here is deviations on upwards of about 20 dB difference between these two, for example. So depending on the room and depending on the microphone and speaker positions within that room, we can end up with very, very different frequency responses due to the room acoustics. So when you superimpose these three frequency responses, what you end up having is certain frequency ranges that have much more gain in the system than other frequency ranges. And those are going to be the frequency ranges that are most prominent to ringing when we get close to this feedback threshold. If we look at a spectrum analyzer of a live sound system with some ringing frequencies, feedback frequencies, typically this is what it's going to look like. You're going to have no sound in the majority of the spectrum except for a few very discrete sine tones ringing. That's typically how feedback manifests itself in a live sound system. So with that in mind, how can we keep feedback down? Obviously, feedback is a terrible thing that we want to avoid, and there's a few things we can do. Most commonly, feedback is generated from the stage monitor projecting sound into the microphones. When we get the front of house system up really, really loud as well, then we might have some front of house sound system sound getting into the microphones and causing feedback as well. But primarily, what you need to worry about is the stage monitors. What you can do is you can orient your microphone such that the null of the microphone is pointing at the speaker. Therefore, not so much sound from the speaker will be making it into the microphone, and the overall gain of that feedback loop might be low enough. If we take a hypercardioid microphone, which actually has a little bit of a back lobe, then you can see that the ideal position for the microphone is slightly different. Another thing we can do, let's say we've optimized our microphone position, we've optimized our monitor position, we've optimized our front of house positions, and we're still getting feedback frequencies. We're turning up the microphones loud enough such that the musicians feel like they can hear themselves, but we're getting feedback frequencies. There's another thing we can turn to, and that's an equalizer. So the idea is we insert the equalizer in the chain between the mixer and the amplifier. So we have a microphone which is picking up a musician. That goes through the mixer. That gets mixed in an aux track, most likely, out of the aux mixer into an equalizer. And then that then goes on to the amplifier and the loudspeaker. And what this allows us to do is equalize the signal on its way to the stage monitor. Typically, for these applications, you're going to see a graphic equalizer in live sound. A graphic equalizer is an equalizer that divides the frequency spectrum up into bands, and ideally, for this purpose, very, very narrow frequency bands. What you can then do with this equalizer is you can find the range of frequencies, the band, that is most closely associated with your problem ringing frequency, and you can reduce it. You apply a very narrow notch EQ to this signal so that we can actually reduce the amount of gain that the system has at that frequency, and most of the time the system will stop ringing at that frequency. Once you've done that, you can add a little bit more gain to the system, and then most probably some other frequencies will start ringing that you need to address. So this is a common part of the process, is setting up your system, turning on your monitors, noticing that there's some feedback frequencies, using an equalizer to reduce those frequencies until frequencies start to pop up in other places, and then maybe reevaluate to see if you have enough gain in your system to satisfy the musicians, but little enough gain in the system to avoid feedback. One other thing you can do, because you can imagine in order for feedback to keep adding and adding and adding at a given frequency, is sometimes instead of putting an EQ here, you can do a simple polarity reversal. And what that does is frequencies that were adding and adding on top of each other before will, as you know, all of a sudden cancel. This can be somewhat effective, but often in my experience what ends up happening is there's just a new set of frequencies that end up being generated and ringing instead of the ones that you had before. The primary way of getting rid of this is most likely an equalizer, and ideally an equalizer with a very narrow notch filter for each feedback frequency. Now, of course, there is one disadvantage to this, is that from now on, that vocalist sound or whoever's coming through the stage monitor, their sound now has this EQ in the past, and it's going to not necessarily sound perfect because of that. But in most circumstances in live sound, you will take a slightly imperfect frequency response over feedback. Next is system tuning. You need to understand the process of tuning a basic front-of-house speaker system, the speaker system that's designed to deliver the performance to the audience. As you know from studying acoustics in rooms and in your electroacoustics class, the sound of speakers in rooms, that if we set up a set of speakers that are perfectly flat in the frequency response in a room that has non-ideal acoustic treatment, then at the listening position, we can expect there to be an uneven, a non-flat frequency response. This is not ideal. Ideally, in the listening position, we would have a totally flat frequency response so that the sounds that we're trying to play over the speaker system are as they are intended. In order to fix that, you might insert an equalizer in the chain. So let's say you have a speaker system set up in a room that has way too much bass. You could use that equalizer to roll off some of the bass. Let's say you have the speakers set up in a room with a ton of high frequency absorption and the high frequencies are just a little lacking. You could use an equalizer to increase the high frequencies a little bit. Let's say you're in a smaller room and there's a really nasty room mode at one of the particular locations, and you're looking to use the equalizer to reduce that room mode so that the system doesn't ring so aggressively at that group of frequencies. In order to do all this, you could do it by ear, but better off having a measurement system. A measurement system most likely is made up of a calibrated measurement microphone and some sort of software or hardware device that can do impulse responses. That impulse response system will need to feed the console. That console will go through your main equalizer, and that equalizer will go to the front of house system. What the computer measurement system will do is most likely play some test signals through the sound system. Those will be recorded by the microphone and analyzed in the software. What you're trying to do here is to achieve a flat frequency response or a close to flat frequency response at as many listening positions as possible. Of course, that won't be doable. You won't be able to get a perfect frequency response at all these positions, but you want to get as close as you can with the tools you have available to you. Finally, microphone splitters. It's important to understand how microphone splitters work and how they are set up and what this means for phantom power considerations. Your most common type of microphone splitter is a passive transformer microphone splitter. The idea is you have a microphone input, so you will need one of these transformer splitters for every single microphone you have in the chain. So most of the time in live sound you can get boxes that have 4, 8, 32 or even more of these mic splitters all built into a single stage box. On the input, you put your microphones. This is your raw microphone signal before it hits anything else. And you can see that there is one path that is completely direct. The microphone input goes straight to an XLR output, untouched. This would be equivalent to having no splitter at all in the chain, just a set of wires connecting the input to the output. Often there will be 1, 2, or even 3 isolated transformer outputs, separate from the direct output. The idea here is we're using the transformer to pass signal from one side of the device to the other, while giving the option to lift the ground, and while giving the option to block DC and only allow AC to pass. By allowing this isolation, you can give the option to lift the ground. One thing about the isolated outputs is they do go through a transformer, and not all transformers are created equal, so unless you have a high quality transformer mic splitter, then the frequency response of these isolated outputs will most likely be non-ideal. You might also end up with some distortion products if this transformer is of particularly low quality at certain frequencies. One other thing you need to consider is because there's a transformer here, you can't feed phantom power to the mic input from one of these isolated outputs. You have these attached to preamps. However, if you send phantom power down here, that transformer is going to block phantom power because transformers do not let DC voltage to pass. Therefore, phantom power can only be provided on the direct output. So in practice, the reason why we use these is so a variety of people can have access to the microphone signals, but set their own preamp levels. For example, you might have a front of house console for the person mixing the sound for the audience. You might have someone doing a recording backstage, and you might have someone on side stage mixing the monitors for the musicians. And perhaps they all want to be able to set their own microphone preamp level. Well, this would allow it. You would put your transformer mic splitter on stage. All the microphones would get plugged into it. Most of the time, the front of house engineer or the monitors engineer will get the direct output. Most likely the front of house engineer. It's important that the mixer with the most mission critical role, and in this case delivering the sound to the entire audience, is the one with access to phantom power so they can do troubleshooting when it's needed. So often this will go to front of house, then you send one isolated output to the recording team, and the other isolated output could go to the monitor engineer, for example. Everyone gets to set their own preamp levels, and if the recording engineer is in another room, and that other room has a different power ground than the ground being used by the live sound system, then you could lift the ground to avoid any potential ground loops or to help with any potential ground loops. That's another big advantage of having that transformer, and another reason to put the recording on the isolated output, because most likely if anybody's going to be on a different powered circuit, it's probably going to be the recording team, whether they're out in the recording truck or in some other room backstage somewhere. You will find these transformer mic splitters as simple boxes, as stage boxes, or sometimes built right into venues. To review, you should understand what monitors are for on stage. You should understand that we have wedge monitors and in-ear monitors. You should understand what their function is, how to set them up, and how to do the routing in order to feed these monitors. You should also understand what feedback is and how it can be generated. You should understand that it only occurs when the gain in a system that has a loop, goes above unity gain. You should also understand how it can be reduced with microphone and speaker position, as well as an equalizer or a simple polarity reversal. You should understand what the process of tuning a basic front of house speaker system is. You should also understand how microphone splitters work and how they are set up internally and how they are used, especially when that comes to phantom power considerations. See you in class.